In this video, we're going to talk about section 10.6, polar equations of Conics and Kepler's laws. We're actually not going to talk about Kepler's laws. We're just going to get right up to the point of being able to talk about them so that you can read about them in the textbook if you want to, because they're not a primary objective right now. So let's go ahead and have the objective today of this video to analyze and write polar equations of conics. Let's recall the standard form, the rectangular form of an ellipse from 10.1 with A being greater than B. If our major axis is horizontal, we have x minus h squared over a squared plus y minus k squared over b squared equals 1, where the center lies at hk, and the major axis has a length of 2a and the minor axis has a length of 2b. Likewise, if the major axis is vertical, we'll have a form of x minus h squared over b squared plus y minus k squared over a squared is equal to 1. Again, the center lies at hk, the major axis is equal to 2a, and the minor axis is equal to 2b. The foci are going to lie on the major axis c units away from the center, where c squared is equal to a squared minus b squared, so c will be equal to the square root of a squared minus b squared. While we're going to talk about all different types of conic sections in section 10.6 in the textbook, and I encourage you to read more, I'm going to focus mostly on ellipses here in the notes because they are typically the type of conic section that we're dealing with Kepler's laws. And so this is a discussion that leads into you being able to understand Kepler's laws. And so we're going to focus mostly on ellipses, since planetary orbits and things like that are most of the time they're elliptical. So the eccentricity E, it's kind of a fancy looking E of an ellipse, is given by the ratio E for eccentricity is equal to C over A. Remember how you calculate C here, and remember what A is. And that's the way you find eccentricity no matter what. But because the focus of the ellipse, the foci of the ellipse are located along the major axis and the center, we know that C, the distance between the center and the focus, has to be greater than 0, but also has to be less than A, because the foci have to be inside between the center and the vertex. So let me just draw a picture here to show you what I'm saying. Here's the center. Here's the vertex out here. This distance is A, and the focus has to be somewhere along this line there. And so it has to be between a distance of 0 units from the center and A units from the center. Since the vertex is A units from the center, it has to be between the center and the vertex. The closer that C and A are to each other, the closer this focus is to that vertex over there, then the closer, is that right? C over, no, the closer that the focus is to the center, if I move the focus closer and closer to the center, and I get closer and closer to 0, that's more and more a circle. So when this point comes this way and comes closer and closer to the center, then I get less elongated and more rounded, and it's going to be perfectly round if F and C coincide with each other. If the foci come and lie right on top of the center there, I'll get a all the points here will be equidistant from the center, and it won't be a distance of A, it will be a distance of R. The quote major axis and the minor axis will have the same length then, because I'll have A squared and B squared will be the same thing. They'll become R squared, and I multiply by it to the other side of the equation, and I have the equation of a circle. All right, the more elongated the ellipses, the closer that the ratio C over A is to 1. That is if F moves this way and gets closer and closer to that vertex. And if I do that, it's getting closer and closer to being a line in this situation where I'm pulling this part down and this part up, and it's getting closer and closer to just being that major axis. But there's going to be another thing that we're going to define in just a second that's going to have an eccentricity of 1, and that's going to be a parabola. And we already know that from its definition, but we'll just remember that because of the way that we've defined a parabola, that C over A is going to be 1, since it's the locus, the set of all points that are equidistant from the focus and the directrix. And we'll start using the directrix to define what the and the eccentricity here to define the shapes. In fact, that's the next thing that we're going to do. So theorem 10.16, classification of conics by eccentricity. Let F be a fixed point, the focus, and we're going to put that fixed point at the pole. And let D be a fixed line, the directrix in the plane. Then let P be another point in the plane, and let the eccentricity, that fancy E, be the ratio of the distance between P and F. So the distance between P and F there, we're going to call that distance PF. And this distance here between P and Q, we're going to call PQ. And our eccentricity here, another way to calculate it if we don't know A and C, is to take this point here, this focus, put it at the pole, the distance to a point from the pole like that, and then the distance from that point to the directrix. And we've only ever talked about a directrix before with a parabola, so let's talk about that again, that all the points P on this curve are equidistant from the directrix and from its focus, and it has one focus there. And in this situation, the ratio of the distance from the focus to the point over the point to the directrix there is less than 1. So it's closer to go from the point to the focus than from the point to the directrix. And here for a hyperbola, the eccentricity is going to be greater than 1 here, which means that that PF right here, this distance from this point to this focus, is going to be bigger than to go from P to Q here. But that ratio is also going to be the same as if I put a point over here on this piece, and I wanted to even look at that focus. There's another focus that's over here. But if I wanted to definitely draw this distance from a point on this piece to that focus, and that directrix is definitely closer right there, but those ratios are actually equal to one another. That's very interesting, whether I use the focus here and a point that's on the piece that's closer to that focus, or whether I use that focus and a point that is on the other piece that is further away from that focus. We're going to get the same eccentricity from any point that's on either piece there, and that eccentricity is going to be greater than 1, and that's going to tell us that it's a hyperbola. All right, so now let's go ahead and look at theorem 10.17, polar equations of conics. The graph of a polar equation is going to be in the form of, for conic, is going to be R is equal to the eccentricity times D. We'll talk about what D is in just a second. Divided by 1 plus or minus E cosine theta. or r is equal to E times d over 1 plus or minus E sine theta. So we actually have 4 cases here. We have the equation being set up with the cosine function, plus or minus. So case 1, case 2 is plus E cosine theta, case 2 minus E cosine theta, case 3 is going to be plus E sine theta, and case 4 is minus E sine theta. Actually, I'm not sure those are 1, 2, 3, and 4 here. Let me tell you, they are not. So this is going to be 1 and 2. Cases 1 and 2 are this piece, and then cases 2 and 3 are this, or 3 and 4 are this piece. But it's important to see here that the eccentricity is greater than 0 here. So let's look. We're not getting any negative eccentricity for any of these pieces here. It's always greater than 0 for an ellipse, a parabola, and a hyperbola. It's not going to be a circle where the eccentricity is equal to 0, right? And d, the absolute value of d is the distance between the focus and the pole and its corresponding directrix. So again, when we write these polar equations, we're going to fix that point F at the pole. And then we're going to use the distance between that point F and the directrix, and that point F and maybe another point they give us, but actually we don't need that for this. We just need the eccentricity given to us. If we need to define the eccentricity, we would need that other point to get that ratio. So if we have a horizontal directrix above the pole, this is just showing this to you with a parabola, then you would have a vertical axis of symmetry here, or a vertical major axis if you had a hyperbola, or not a hyperbola, an ellipse. You would have a situation that would, you know, trying to draw it here, but you'd have a situation that might look like this, where you're opening away from this directrix, and there's that focus, and there's another focus down here, something like that. If you have a situation like this, you might have a focus here, a directrix down here for an ellipse, and it's going to open like this, and that's still going to be a vertical major axis there. The directrix is going to be perpendicular to your major axis or your axis of symmetry. So that's kind of an important idea. You see I've got kind of bad drawings, but oh well. Here the major axis is going to be horizontal, and your foci are going to lie along that major axis there. And in this one, you can see that your major axis is going to be horizontal, or your axis of symmetry, and your foci will lie along there. Remember that a ellipse is going to have 2 foci, so does a hyperbola, but a parabola only has 1 focus. Yeah, let's come on back up here. So this is case 1, 2, 3, and 4 right here. So case 1 right there, r equals ed over 1 plus E sine theta, where your directrix is above your focus that's at the pole. And here is r is equal to ed over 1 minus E sine theta, where your directrix is below your focus that is at the pole. And then here is r equals ed 1 plus E cosine theta, where your directrix is to the right of your focus that's at the pole. And here is r equals ed over 1 minus E cosine theta, where your directrix is over here to the left of your focus that's at the pole. So let's do an example here. Best drawing that I could do, freehand. So we're going to find the polar equation R of the conic with its focus at the pole right here, and an eccentricity of 1/4 and a directrix of y is equal to 4. So I drew that directrix of y equals -4, y equals a -4 down here. Eccentricity of 1/4 is less than 1, so we know that this is an ellipse. That's what I was trying to say there parenthetically, is we know that it's elliptical in shape, and our distance here from our focus to our ellipse, to our directrix for our ellipse, that we'll call it d. The absolute value of d there is 4. And so r is equal to 1/4 times 4. Just call this d. D is 4. 1/4 times 4 over 1 minus 1/4 sine theta. So we're going to take 1/4 times 4 is going to be 1. 1 over 1 minus 1/4 sine theta. And we don't like leaving fractions in the denominator, so I'm going to multiply by 4 over 4 to clean this up. 1 times 4 is 4 over 4 minus sine theta. And that's it for this video. And that's it for our Calculus 2 topics. And hopefully I'll see you again for one of the other topics that's upcoming from Calculus 2. You can go on to linear algebra, differential equations, or Calculus 3. And hopefully all of those videos will get made in the near future for you. Be on the lookout for those. Also be on the lookout for supplemental examples for Calculus 2. Hopefully you've seen them already. If you're at this point, we'll have some supplemental examples that are from the Larson textbook, and we'll have some supplemental examples that are from the Briggs textbook as well. All right, hope you enjoy, and good luck on your final exam if you're at this point in the videos.